Now what we can do now is we can actually, also simulate NMR spectra. So to do that, right, we have our molecule right here that we've already optimized, right? We've already done the vibrational frequency calculation to make sure that we're in the ground state. And so what we can do is to set that up, right? We go here under these conditions, we can go to calculate, right? So let me just change the name right here, right? So this is NMR, is what this computation is going to be. And so if we scroll down here to the bottom, right, we can, do the proton and the carbon NMR. So we select that. So we select our method, right? So in this case, we're going to be using def2tzvpp. And then we are also going to add the auxiliary basis set into it as well, right? This one right here. Then here under advanced, one thing that we definitely have to do is we have to either have the def2jk or the auto aux checked, right? And so the def2jk is if you're using any of the def2 basis sets. That's the one that you would want to select. For every other one, right, you would want to hit the auto aux and make sure that you're using that. And so again, also making sure that we're adding, the number of cores that we're looking at, and then we can submit this job. So now if we look at our completed NMR data, right, we can go down here to calculated quantities, right? So we're going to get our absolute NMR shifts. Now, if we're looking at this data, right, we have our carbons, we have our hydrogens. We're going to notice a few things, especially here with the hydrogens, right? These hydrogen atom values are pretty high up there, right? The ppm shifts are, 21, 29, 29, 29, right? Those are dramatically different from what you would expect to have in these instances. And so, you would expect, especially right, considering right, we're looking at a methyl group and the aldehyde, right? The methyl group probably somewhere in the 1 to 2 ppm region, right? This aldehyde probably in the 8 to 11, depending on everything else in those cases. So these are kind of off, and that has to do with the fact that NMR spectra are also referenced to a reference compound. So when we're talking about any of those shifts, we're actually referencing it to tetramethylsilane, right? So TMS for short, right? That's what we always set all of our NMR spectra to as 0. So what we want to do to be able to do that same referencing and having the scale be what we want, we actually also need to calculate now what the DFT parameters, right, in the NMR spectrum of TMS using DFT, right? So if we now go back to our job manager and we just set up a new calculation, what we can do here, right, is we can build that. So, TMS is just simply a silicon atom in the middle, and then you have 4 CH3 groups that stick off of it. So it's going to change that central atom to a silicon. We can do cleanup, right? We have mechanics, and so now looking at it, that looks kind of like messy. So let's try that again. So cleanup, maybe idealized. There you go, right? So now that kind of looks better, right? So that you can either do mechanics or idealized, and make sure you always check to verify that the geometry actually matches what you would expect the geometry to actually look like. So now what we have to do is go through the normal steps that we would traditionally do. So in this case, we're looking at TMS. So the first thing we have to do is a geometry optimization. And we're going to have to use and make sure that we're using the exact same basis set and auxiliary set and so forth, all the exact same parameters that we used for other calculations, right? So we're using def2 B3lip, tzvpp, right? Change that auxiliary basis set to tzvppc, right? Go here, change the number of nodes to 32, right? And so the def2jk, you would only want to have that clicked if you're going to be doing an NMR for all of our purposes. Now that the vibration calculation is completed, what we can do is we can look at it and make sure that we're looking at the output file. So if we check for vibrations, right, we can see that we're in a ground state minimum because we have 0 negative vibrations here, which is great. So we can just simply set up now our NMR calculation. So we just change that here, right, to the NMR corrected. Right, B3lip, tzvpp, tzvpp/c, then under advanced, make sure that we hit def2jk, make sure that's enabled, and we just start it. And now we just wait for this to complete. So now that the computation is finished, right, we can look at it. And the most important part, right, is if we look here at the NMR shifts. Now, what we want to do is actually pull up an Excel file. And what we can easily do, so if we're looking at it, right, we can see not all of the shifts are exactly the same. For the proton, right, not all of the shifts are exactly the same for the carbon, which makes sense, right, because they're not truly in a perfectly symmetrical environment where all of the different bond lengths and angles are all exactly the same. In an actual NMR solution, right, everything is dynamic. All of the methyl groups are constantly rotating. Everything is moving around. So things kind of balance out at, room temperature so that they all end up being the same. Whereas what we're looking at right now is a gas phase, snapshot in time picture of our molecule. And so what we have to do in this case, right, to figure out what we should be referencing is to just simply take the values that we have, right? So we can take for the carbon, we can copy those directly here into the Excel file. And we can do the same thing for the hydrogens. So if we take these and we copy both of these over, right? All we have to do is just simply take the averages, because we know that all 4 of the carbons should be exactly the same, right? All 12 of the hydrogens should also be exactly the same. And so the values that we should get, in this case, if we average it all out, should be what the TMS shift should be for the shielding. So if we, just simply go and average that in this case, so we get that value. And then in the case of the hydrogen, same thing. Right, so we have both of these values right here. So what we can do now is if we go back to our NMR calculations, right, so we can look at the acetaldehyde, and we go here. So now if we go down to the absolute NMR shifts, what we can do is we can take that value that we had just put it, calculated within Excel. So we take the carbon one right here, the 183.9845. We can copy that into the TMS shielding for carbon. We can do the same thing for the hydrogen. We can put both of these in here. And so now we just simply click the button, right? And it's just simply going to now adjust the peaks. And what we can see here, right, is that we have for the 3 hydrogens, right, that are off of the methyl group right here, right, 7, 6, and 5. These have, shift values of 2.1748, 2.1758, and 1.9238. Now again, right, because we're looking at what's essentially a snapshot in time, not all 3 of those hydrogens are truly equivalent, right? The 7 hydrogen is, directly in line with the carbonyl group, so we would expect that to be different from the both 5 and 6, which is what we see in the computed value. So then in real life, what would happen in these cases, right, is constantly rotating, so you actually end up averaging out all 3 of those values again, right? If you were to try and compare it to, the traditional values that you have from an experimental thing, right? And then here also, right, we can see the hydrogen, right, that's off of the carbonyl, right? The aldehyde hydrogen, right, comes in at 10.2, which is also what we would expect. And then same thing here, right? We can see that for the carbons, that the carbonyl carbon is at 203, and then the carbon, right, the methyl group carbon 1 in this case is 33.6885. So, those values all match up with what we want. And what we can also do is we can simulate the spectra, right? So if we just click on that right there, right, we can see that, we would expect 2 peaks, in the case of aldehyde showing up there. And then same thing, if we look at the proton spectrum right here, you get 2 different groupings. And so one thing to kind of point out is that the WebMO software goes in and it automatically throws in this hypothetical coupling, so you can change what the coupling value is, right? Because that always depends upon the J coupling and interactions between the different protons. You can also change the Nmr Field, which will also affect the spectrum a little bit. So if you're trying to, do some comparisons of your computed values and spectra with experimental values, right, you can alter these to kind of have things line up. And then same thing, right, with the peak width. You can also change the peak width, make it, broader or closer together. But this is what you would expect the system to look like, right, that you would have your aldehyde being essentially a quartet. And then you would also expect, the methyl group to come in at being essentially a doublet, right, based off of our NMR rules. And again, you can just simply save the image right here, or you can export that data so that way you can work it up in like Excel or something along those lines. But yeah, so that is how you can simulate your NMR spectra of a molecule. One other thing that you can do as well, so, if you've calculated the NMR or the IR, there are a lot of databases that exist where you can actually look up and compare your values. And so that's actually kind of built in here to WebMO, where if we go to look up right here, we can actually go to databases, and it has all these different databases right here that give you access to different components of it. So one of the databases is Nmr Shift DB. So if we click on that, it'll take in the molecule that we have, and it'll actually show us what the shifts that we should be expecting for the different atoms and what the spectrum should look like. So we can see right here that in the case of the carbon NMR, they're expecting a peak at 200.5 and 31.2, which if we look at what we have here, right, we have 203 and 33. So that's not a bad comparison. Same thing here. We can look at the proton spectrum, and so what we can see is that they're anticipating 9.7 and 2.1, and so we're getting 10.3 and 2.2, which is again pretty close. So that's one of the databases you can look at. Another database that you can look at is the SDBS database, and so you may be familiar with this database if you've encountered it in Chem 360. But what it does here, right, is it directly should take you to your molecule. In this case, it didn't because I had to do the whole login thing. So if I go here again and I try it again, because you have to accept their terms for using their website, it should go directly, right? So now here it's simply showing me the two different options, right? So it has acetaldehyde and it has ethylene oxide. And so we're using acetaldehyde, so we can look at the proton NMR here that they have in their database. And so looking at this database, right, what we have again is that the expected shift is at 2.02, and that you have the aldehyde is at 9.789, and here, right, it tells us that we should probably expect to have a J coupling of 2.9. So if we wanted to, we could go back here and we can change this J coupling value to 2.9, and we can look at the spectrum again, right, to kind of get an idea of what it would look like more closely in that case to what we have here. And same thing if we look at the carbon NMR, right? The carbon NMR, when that loads up, right, we're expecting a peak at 199.93 and 30.89. And so what we have here, right, is 203.33, right? So we're off by about 3 ppm, which isn't, a terrible thing for the carbon in these cases. So, those are some of the tools that you can use within WebMO, comparing both your computed spectrum with known data that exists in databases out there.